Welcome back, students. In this video segment, we will talk about the last really heavy involved section involving vector spaces for this chapter, section 2.4, entitled Dimension, Null Space, row space, and column space. In this section, we continue on examining the structure of vector spaces. And then we look at three very popular, very common, very important vector spaces called the null space, the row space, and the column space. So I want to bring to mind something that you probably noticed happening as you went through homework in section 2.3 and earlier. We noticed that in previous examples that it appears that bases for R2 have two vectors, and the standard basis is a perfect example, and for R3 there are three vectors. Again, the standard basis is a good example, but other bases for R3 tended to have, in fact they always had three vectors. And that any more than two vectors in R2 turned out to be linearly dependent, so they didn't form bases. And more than three vectors in R3 were linear dependent and thus didn't form bases. So this generalizes. This is in fact something that happens in general, and we start with a statement of that fact, or at least partially a statement of that fact, by way of, in your textbook, is called Lemma 2.8. Lemma 2.8. It says that if V1 through Vn form a basis for a vector space V, then every set of vectors W1 through Wm in V, where m is more than n, are linearly dependent. So let's tear this apart. This is a very important statement here. So if V1 to Vn, n as in Nancy, form a basis for a vector space V, that means we have n vectors. We happen to have n vectors that form a basis for a vector space. Then every set of other vectors, W1 to Wn, m, where you have m vectors in that set, where that set contains more than the set of v vectors, has got to be linearly dependent. It sounds much more complicated than it really is. What this statement says is something very profound with respect to vector spaces. What this statement says, in other words, that if n vectors form a particular and I have written here form a vector space, and it's not correct, form a basis for a vector space, then any set of more than n vectors is automatically linearly dependent. Let's take a look at that again. If you have a basis that has three vectors in it, if you have a basis that has three vectors in it, then any set of more than three vectors is in that same vector space is automatically going to be linearly dependent. And we saw that in R3. If we have a set of four vectors in R3, those four vectors are automatically linearly dependent, okay, because there is a basis with three vectors in it. Okay, so if you have a basis with a certain number of vectors in it, any set of more than that number of vectors is automatically linearly dependent. You're not responsible for the proof of this. I used to have my students prove this, but I think it's a little much, especially since they're doing stuff online now. Okay. We get more. We get more than this. We get something even more specific than this by way of Theorem 2.9. So here's Theorem 2.9. If V1 to Vn and W1 to Wm both form bases for a vector space V, then n must equal m. This is a much more direct statement of the lemma, I think. The translation of it is that all bases have exactly the same number of elements in them. This I'd like you to see the proof for. Okay, so here's a proof. It's a very simple proof, actually, based on the lemma that we just looked at. So let's start with two bases. So let's let v1, v2, all the way up to v sub n, as in Nancy. Let's see, like clean this notation up a little bit. v2 up to vn as in Nancy, and w1, w2, all the way up to wm, m as in Mary, form bases. So we start out with two bases for V, a vector space. What I want to show is that n and m must be equal. They must be the same number of vectors in these bases. Okay, so proof. Case one. Case one. Well, we have two bases. There are only three possibilities for m and n. Either m is more than n, or n is more than m, or m and n are what? Are equal. So case one. Suppose that m is more than n. That if m was more than n, that would imply what? It would imply that the w's are linearly dependent by lemma 2.8. That would imply that the w's, w1, w2, all the way up to wm, are linearly dependent, and hence don't form a basis. Okay, so, well, we're starting out with two sets of vectors that are bases. So this shows that m can't be more than n. That would mean the w's don't form a basis because they would be linearly dependent. That's kind of contradicting our assumption that we do have a basis. So the next case, case 2, is that n is more than m. That there are more v's than w's. Well, that implies that v1, v2, all the way up to vn are linearly dependent. Both of these cases are as a direct result of lemma 2.8. And that would be impossible because we're assuming that v1 to vn form a basis, and half of the definition of basis is that they're linearly independent. So we've shown that m can't be more than n and n can't be more than m. So the only conclusion is that m and n should be equal. QED. This is an extremely powerful theorem. It says that every basis for a vector space has exactly the same number of elements in it. Okay, that leads us to probably the most important part of this section. We're going to talk about three very important subspaces or vector spaces, but the concept coming up, the concept that results in the concept that we define, given that all bases have the same number of elements in them, is really the concept that holds the section together. So, definition. Okay. If a vector space has a basis, if a vector space has a basis with n vectors, we say the dimension of V is n. So n, the number of vectors in every basis for a vector space, is called the dimension of the vector space. Well, this is probably the first time in your life, unless you've studied vector spaces before, where you've had an actual precise definition of a term that we use every day. We talk about 3D, 2D. The D is the dimension. The dimension is the number of vectors in every basis for whatever vector space you're in. So flat space, if you will, R2 is two-dimensional because there are two vectors in every basis for R2. In three-dimensional space, the space that we live in, is three-dimensional. I think I just said that. the 3D, the space that we live in, is called three-dimensional because every basis for R3 has three vectors in it. Okay, we write dim v equals n. Okay, so let's look at some popular vector spaces and a couple of examples along the way. So example, what's the dimension of R2? We basically did that. It's 2. Okay, we have the standard basis vectors, which include the column vectors 1, 0, and 0, 1. So every basis for R2 is going to have two vectors in it. So we have the dimension of R2 is 2. So what's the dimension of Rn? Well, pretty obvious. That would be n. What's the dimension? Let's get a little more complicated or a little more involved. Vector space of the set of all 2x2 matrices with real entries. Set of all 2x2 matrices. What's the dimension? Well, if you think back in the last section, that's got to be 4. Remember, we have a basis. The basis is the set that contains E11, E12, E21, and E22. Those four 2x2 matrices from the last section. There are four matrices in that set. There are 4 vectors in that basis. So the dimension of the set of all 2x2 matrices with real entries is 4. So what do you suppose the dimension of the set of all m by n matrices with real entries is? It is m times n. Okay, you can form the standard basis for this vector space by putting sequentially 1 in one space in one entry and zeros in the rest of the spaces. And if you consider every possible matrix where that happens, every possible m by n matrix, you have m times n matrices. Okay. Okay, so what's the dimension? What's the dimension of P2, the set of all polynomials of degree 2 or less? Well, think about our basis for that, a basis for that. A basis would be the set of all the set of vectors 1, x, and x squared. This set forms a basis. There are 3 vectors in that set. So the dimension of P2 is 3. So what do you suppose the dimension of Pn is? The set of all polynomials of degree less than or equal to n. Should be n plus 1. Okay. Standard basis vectors for Pn: 1, x, x squared, x cubed, all the way up to x to the n. Okay. So let's look at a little more complicated one. Even though it's a very simple vector space, let's look at the dimension of the set of the vectors that only has the 0 vector in it. I'm not saying matrices or polynomials or vectors from Rn or whatever. Just you have a 0 vector. The set that only has a 0 vector definitely forms a vector space. Well, what do you suppose that I always hear the wrong answer, by the way, so that's a hint that's got to be a little tricky. The wrong answer is, well, there's one vector in there, so if you're going to have a basis, you would think it would have to have that vector in it, so you would think 1. And the answer is 0. This is called the zero vector space, and the zero vector space does not have a basis. Okay, just because we have a vector space doesn't mean we have to have a basis. This vector, let's back up a little bit. The zero vector space doesn't have a basis in it. Why? Well, if it were to have a basis, it would have to be the vector. It would have to be the set that just has the zero vector in it. That's the only possible thing you could have, set you could have for the basis for this vector space. But you did a homework problem. Well, you should have done a homework problem in section 2.3, number 27, that says any set containing the zero vector is automatically linear dependent. So you should look back at your proof on that, or look back at my proof if you use the write-ups for that. So I'm not sure if I posted the homework for 2.2. I think it was 2.2. Maybe it was 2.3. Any set, in any case, number 27 on it's 2.3 on page 94 says that any set that contains the zero vector is automatically linearly dependent. Okay. Well, I think we have a little time to actually look at that. So let's show that the dimension of the zero vector space must be 0. Let me do this in red. Any set that contains the zero vector is automatically linearly dependent, okay, and thus couldn't form a basis, because half of the definition of a basis is you have linear independence. Okay, let's look at a real quick proof of that. Let's see. Let's let C1, C2, all the way up to Cn. Oh, not C's, sorry. These should be vectors. Let's let V1, V2, all the way up to Vn. Let's see. Bn elements of, I have a hard time writing today. The elements of V, a vector space. So now consider the set 0, V1, V2, V3, all the way up to Vn. So now I've taken a set of vectors, n vectors from a vector space. Now I'm plopping the zero vector in with that set. And I'm going to show that that set must be linearly dependent, no matter what the vectors are, v1 to vn. If you put 0 in there, if you add another vector 0 in there, you automatically have a set that's linearly dependent. Here's the proof. What has to happen for linear dependence? So we have to set up the equation. Let me put an arrow over the zero vector. C0 times 0 plus C1 V1 plus C2 V2 plus ... plus Cn Vn equals the zero vector. And for linear independence, the only possible constants that can result are 0. However, notice that C0 equals 1, and then the rest of them, C1 equals 0, C2 equals 0, etc., all the way up to Cn equals 0, work in this equation. They satisfy this equation. If you put C0 equals 1, the scalar 1 times the 0 vector is the 0 vector. And if you put all the other constants, C1 through Cn, as 0, they work in this equation. That is, there exist constants C0, C1, all the way up to Cn, not all what? Not all 0. Such that C0 times 0 plus C1 V1 plus C2 V2 plus all the way up to Cn Vn equals the 0 vector. That's the definition of linear dependence. That is the set 0 V1 containing V1. I don't have to put arrows over the V's. V2 all the way up to Vn are linearly dependent. QED. So I did a homework problem for you. This is homework to problem number 27 again on page 94. It says that any vector that has the 0, any set of vectors that has the 0 vector in it must be linearly dependent. So back to our vector space, the vector space that only has the 0 vector in it. It can't have a basis, because any basis would have to have it and only it in it, but it is the 0 vector, so it is a linearly dependent set. Okay, let's take a look at another example here. Let's take a look at identifying the dimension of P, the set of all polynomials. Not of degree less than or equal to n, but the set of all polynomials. Includes third degree polynomials, 500th degree polynomials, 1,000,000th degree polynomials. The dimension of this vector space is infinity. A basis for this vector space has an infinite number of vectors in it. It has 1, x squared, etc. Has all the powers of x. So there are infinite number of entries or elements in this vector space, or vectors in this vector space, basis rather. So the dimension of P is infinity. There are a lot of vector spaces that have their dimension infinite. So other common vector spaces with dimension infinity are set of all functions defined on an interval, the set of all continuous functions on an interval, the set of all differentiable functions on an open interval, the set of all functions that have continuous derivatives of all orders on AB. The dimension of each of these vector spaces is infinity. Okay, so if a vector space has a basis with a finite number of vectors in it, it's called finite dimensional. Okay, so if a vector space has a basis with a finite number of vectors in it, it is called finite dimensional. Vectors that don't have a finite number of vectors in them are called infinite dimensional. Most of the time, we're going to be looking at examples with finite dimensional vector spaces. But we have common ones, the ones mentioned before, the functions, continuous functions, differentiable functions, etc. Even just the polynomials, they are infinite dimensional vector spaces. Okay. All right. Now, Working with vector spaces is hard. You've discovered that. If you've had a chance to get through the homework problems, homework sections up to through 2.3, you've discovered it's tough. It's really, really grueling sometimes, sometimes tedious, but difficult to deal with vector spaces and proofs and stuff like that. Anyways, we get some relief. We noticed as we were determining whether vector spaces were formed that we had some similarities in the two things that define a basis for vector spaces. Remember, we have a vector space. A set of vectors forms a basis for a vector space if those vectors are two things. They are linearly independent, and if they span the vector space. Well, when we were showing linear independence, we discovered that right after that, in the proof of spanning, we ended up with a similar result, or a similar type situation. Very often, in fact, most often when we were showing linear independence, the linear independence of a basis depended on whether we had a solution to a homogeneous system of equations. And right after that, spanning involved a system of equations with the same coefficient matrix. And very often we were able to do both of those things by looking at the determinant of the coefficient matrix. And in any case, it seems like if we have linear independence, then spanning should follow automatically, and vice versa. Well, that's actually true. That's our next major theorem here, Theorem 2.12. Theorem 2.12 from our text says that suppose that V is a vector space and with a dimension n. So let's suppose we have an n-dimensional vector space V. Then, 1, if V1 to Vn are linearly independent, then those same vectors form a basis. What's missing from that? The spanning. We don't have to show spanning. If we know the dimension of the vector space is n, and we have n linearly independent vectors, then those n linearly independent vectors automatically form a basis. That's amazing. That's really amazing. Also, number 2, if we have n vectors that span V, then those n vectors form a basis as well. Okay, we don't have to have 1 and 2 holding true. It's just one or the other. If we have, but the kicker is, the only thing holding us back is that we have to know that the dimension of our vector space to begin with. Okay, we have to know the dimension of the vector space to begin with. We have to know the number of vectors in any basis to begin with. Once we have that, then all we have to have are n vectors, and those n vectors are either linearly independent or span. We don't have to show both things. So in R3, for example, if you find 3 vectors that are linearly independent, boom, they automatically span the vector space and we have a basis. Okay. If in R2 you have 2 vectors that span R2, boom, you automatically get linear independence and you have a basis. That's going to prove to be really helpful for us in our quest to determine whether we form bases or not. So here's a specific example. Don't know why I'm in red. So specific example. Show that the vectors x squared minus 1, x squared plus 1, and x plus 1 form a basis for P2. Okay. Well, let's use Theorem 2.12. The dimension of P2 is 3. We know that. The standard basis vectors 1, x, and x squared form a basis, so we have the dimension is 3. So any set of 3 linearly independent vectors automatically form basis. We don't have to show spanning. We don't have to show the second thing. So let's test for linear independence. Why not spanning? Spanning tends to be a little more difficult than linear independence. Linear independence generally ends up with us having to determine the nature of solutions of a homogeneous system, whereas spanning, we have the same system. The same coefficient matrix, but the system has constants that are not zero. Okay, not only are they not zero, they're arbitrary. So we can't just shove the system in our graphing calculators and look for a solution and so forth. So anyways, let's take a look at linear independence. We set up the equation that needs to be examined for linear independence. We have C1 times the first vector plus C2 times the second vector plus C3 times the third vector, and we set that equal to the zero vector in P2. Okay, this results in a system gathering the coefficients of x squared. We have C1 plus C2 must then equal 0, and gathering up the coefficients of x, there's only one. C3 should equal 0, and gathering the coefficients of the constants, we should have, we should have minus C1 plus C2 plus C3 equals 0. Okay, and let's take a look at the determinant of the coefficient matrix. This is a square system, 3 equations, 3 unknowns, 1, 1, 0, 0, 0, 1, negative 1, 1, 1. That determinant equals negative 2. I put it in my calculator, and it's not 0. Okay, so the determinant not being equal to 0 guarantees us a unique solution. But every homogeneous system has the trivial solution. So the homogeneous solution, so we should say, so the homogeneous system has unique solution. This is minimum explanation, by the way, for your exams and so forth, and your homework too. Has the unique solution C1, C2, C3 all equaling 0. Okay, we've shown that if we set up the vector equation for determining, I'm having a hard time with my surface. If we set up the vector equation for determining linear independence, that the only possible constants are C1, C2, and C3 equaling 0. That's linear independence. Okay, that implies that the vectors are linearly independent, and that implies they form a basis. By Theorem 2.1.2. We don't have to show spanning. Okay, so we're going to conclude our section, or our lecture, our video segment, with a technique for finding bases for 3 very important subspaces that are associated with a matrix, a given matrix. Okay, one of these vector spaces we've looked at already. Okay, all 3 of these subspaces start out with an M by N matrix. So let's let A be an M by N matrix. Okay. Let's consider the set of all X in Rn such that Ax equals 0. m by 1. Okay. So let's take a closer look at what this set involves. If A is a matrix, an m by n matrix, then Ax equals 0, where x is in Rn, is nothing more than a representation of the most general homogeneous system of equations with m equations and unknowns. This is nothing more than a set of all homogeneous systems with A as its coefficient matrix. Okay, so it's really the set of all homogeneous systems. Since I didn't specify what m and n were, this is just a set of all homogeneous systems of linear equations. Okay, we have a very special name for this set. This set is called the null space, N-U-L-L-S-P-A-C-E, null space of the matrix A. So the null space of a matrix is the set of all solutions to the homogeneous system Ax equals 0, where A is a given matrix. We have a special symbol for this. We call it capital NS of A. The null space of a given matrix is the set of all x and Rn such that Ax equals 0. It's a set of all solutions to the homogeneous system for where A is the coefficient matrix for the system. Okay, so let's examine how to find the basis for the null space. Okay, so just through an example, it's very procedural. There's not that much to it, or any of these three subspaces. The last one's a little more complicated than the other two, but they're not so bad. So here, find the null space. Find the null space of A if A is the following matrix. It is a 3 by 4 matrix, whose columns are 1, 2, 5, 1, negative 3, 0, negative 5, 25, and 10, and 5, negative 30, and negative 15. Okay. So this is the matrix. This is the 3 by 4 matrix. And if I'm solving Ax equals 0, so consider the system Ax equals 0, then since A is a 3 by 4, that means that X has to be a what? A 4 by 1 entry. So X is right out of R4. Okay, so it's going to have 4 variables, and the 0 vector will be a 3 by 1 0 vector. Okay, so consider the system Ax equals 0, and the first step, and I think I'll start labeling these steps here in a nice new color. Step 1, solve Ax equals 0. Solve the system. Simple as that. And we have the Gauss-Jordan elimination method to help us along the way. So we set up the augmented matrix 1, 2, 5. I'll set it up for us. 1, negative 3, 0, negative 5, 25, and 10, and then finally 5, negative 30. I'm mentioning the columns here, and 0, 0, 0. So there's the augmented system. If we produce the row reduced echelon form, or reduced row echelon form, we end up getting 1, 0, doing rows now, 2, negative 3 and 0, 0, 1, negative 7, 8 and 0, and finally 0, 0, 0, 0, and 0. Okay, now keep in mind we're looking for a basis for the null space. Okay, we're looking for a basis for the set of all solutions to the system. So we really need to solve the system. So what does the final matrix tell us? It tells us that x1 plus 2x3 minus 3x4 should equal 0. It says that x2 minus 7 x3 plus 8x4 equals 0. Okay, so we have an infinite number of solutions. Since our last equation can be interpreted as 0x4 equals 0, it looks like we have an infinite number of solutions here. Okay, well, the coefficients of the leading ones, they give us the free variable, they give us the dependent variables, and then the three free variables have to be x3 and x4. So let's solve. This tells us that x1 then should equal negative 2x3 plus 3x4, and x2 should equal 7x3 minus 8x4. Okay, where x3 and x4 are free variables, so they're real numbers. Keep in mind, we are looking for a basis for the solutions. We are looking for a linearly independent spanning set for the solutions. Okay, so step 2, now that we have a solution, find a spanning set. It's 2, find a spanning set. Find a spanning set. Okay, that's not going to be so rough. Let's take a look at a typical solution vector. Okay, so the solution, our capital X, is an element of R4. X1 is negative 2x, let me do this a little neater. X1 is negative 2x3 plus 3x4. X2 is 7x3 minus 8x4. X3, let's do this. X3 and x4, that's okay. X3 and x4 are free variables. Okay, so there's our solution in terms of a vector from R4. Now we're gonna do something that's gonna happen really commonly as we go through these kinds of problems. I'm going to tear this vector apart into the sum of two vectors. I have the operations of addition and scalar multiplication on R4 that allow me to do this. Gather the x3s into a column vector. Gather the x4s into a column vector. If you're not convinced that that's correct, just add them together. You get the single column vector solution by adding these two together. Now, in the first vector, we can factor out an x3. X3 is a free variable. Look what's going on here. X3 is a free variable. It's an arbitrary constant. X4 is an arbitrary constant. Look at what's going on here. Looking for a spanning set. You're looking for a set of vectors such that every solution is a linear combination of those vectors. Every solution is a linear combination of those two vectors, negative 2, 7, 1, 0, and the column vector 3, negative 8, 0, 1. So, the null space of A, that's the set of solutions to the homogeneous system, is spanned by, I just found a spanning set, is spanned by the two vectors, negative 2, 7, 1, 0, and 3, negative 8, 0, 1. Now I don't get linear independence automatically. I don't know the dimension of my vector space, dimension of the solution space. I don't know that. If I did, then if I knew the dimension of the solution space was 2, then I have 2 spanning vectors by theorem 2.12. I automatically get linear independence, but I don't know any dimension yet. Okay, so part 3 was to find a spanning set, and I'm sorry, I think it was number 2. Number 2 is to find a spanning set. Number 3, show linear independence. This is the second part of basis. Okay, now this is not going to be difficult. Remember, we started our concepts of linear dependence and independence by saying that we have linear dependence if one vector can be expressed as a linear combination of the others. Okay, linear dependence. We have linear independence if that can't be true. I cannot write that second vector as a constant multiple of the first. It's impossible. It's impossible. So you could do this. You could say C1 times one vector plus C2 times the other vector equals 0 vector, and then show that C1 and C2 should equal 0. It's simpler just to say that one is not a linear combination of the other. Easier, so we only have 2 vectors here. Easier, one vector is not a linear combination of the other. One vector is not a linear combination of the other. Clearly, I can't multiply the first vector by something and get the second vector. Okay, there's a shorthand term for this. Shorthand, and it only works for 2 vectors. Way to say this. Okay, keep in mind what I just said. There's a shorthand way of saying this, but it only works for 2 vectors. It's fairly common for students to try to use this terminology for 3 vectors. There's no such thing. Okay, shorthand way to say this is the vectors are not proportional. The vectors are not proportional. V1 is proportional to V2 if V1 is a scalar multiple of V2. It only works for 2 vectors. Okay, so and you're allowed to use this. You could show linear independence by setting up the linear independence equation and showing that the constants are 0. That's a monumental waste of time, since you could just observe the 2 vectors are not proportional. Okay, so the vectors are linearly independent. Clearly, this is what you would state. Clearly, these vectors are linearly independent since they are not proportional. Okay, and that forms our basis. Okay, so they form a basis for the null space. The null space of the given matrix. The null space of a given matrix is not a difficult thing. It's just a set of solutions. It's just a set of solutions to the homogeneous system where the matrix is the coefficient matrix. Now I'm gonna mention the dimension of the null space because it's going to be important in about 20 minutes or so. What's the dimension of the null space of A? Well, how many vectors are in its basis? 2. The dimension of a vector space is the number of vectors in any basis for a vector space. So notice that the dimension is 2, and it also corresponds to the number of free variables. Also equals the number of free variables. There were x3 and x4. Okay, this is always the case. Okay, so this will become an important item in about maybe 15 minutes or so. Okay. Okay, so let's take a look at some terminology before we dig into our second subspace related to an m by n matrix. So terminology. A matrix A is row equivalent to a matrix B. I think we've seen this terminology before. A matrix A is row equivalent to a matrix B if B is obtained from A by a finite number of elementary row operations. Those same elementary row operations that were used in Gaussian elimination and the Gauss-Jordan method. Okay, just as a reminder, we can switch rows. We can multiply a row by a constant, that's number 2. And number 3, we can replace a row by the sum of itself and the multiple of another row. Okay, so those are the elementary row operations referred to. So if you take a matrix A and do 1 or 1,000,000 row operations to it to get another matrix B, that B is called, or rather the two matrices are called row equivalent. So matrix A is row equivalent to a matrix B if B is obtained by doing any number of, as long as it's finite, number of elementary row operations. So let's go dig into our next subspace. We're still considering the m by n matrix A. So let A be an m by n matrix. We just finished looking at the null space of A, the set of all solutions to the homogeneous system, where A is the coefficient matrix. Now we have something called the row space of A. You see, the rows of A individually, those are elements of Rn if we view them as row vectors. So the row space of A is the subspace of M, the set of all 1 by n matrices with real elements spanned by the rows of A, the subspace of Rn basically, spanned by the rows of A. So let's take a look at what we're talking about. I want to do two things. I want to make sure you understand what we're talking about, and then I want to show you a really nice 4-step procedure for finding the basis for the row space. Okay, so example, let's let A be the same matrix we had before, same matrix we used to find the null space. So the question is, or the problem is, to find a basis for the row space of A. Okay, well, the row space of A is the subspace of Rn, or the set of all 1 by n matrices with real entries, spanned by the rows of A. So the row space of A is the span of 3 vectors. It's the span of 1, 1, -5, 5 row vectors, 3 row vectors. 2, -3, 25, -30, and 5, 0, 10, -15. Okay. I reached the end of my of my surface here. So it's nothing more than the set of all linear combinations of the 3 rows of A. Okay. Now, you think it would be very simple just to pluck off those 3 vectors as your basis, since everything in this span is a linear combination of these three row vectors, you would think, well, just pick those three. The problem is linear independence. The problem is linear independence. So the issue in picking these three vectors as a basis is not spanning, because the span of these three vectors is the whole vector space. The issue in picking these three vectors as a basis is whether they are linearly independent. We need two things for a basis: linear independent and spanning. Now we're gonna look at a very, very useful theorem that will allow us a nice procedural way to not have to deal with determining whether the three vectors are linearly independent. Because what if they're not? We still need a basis. Okay, so the theorem that's going to help us do this is in your textbook. It's Theorem 2.13. So here's Theorem 2.13. It's kind of an amazing theorem. If A and B are row equivalent matrices, then the row space of A equals the row space of B. Now look what that's saying. If you reduce A to RREF, and the RREF is B, then the row space of the original matrix is equal to the row space of that reduced matrix, that row reduced matrix. Okay, now it's possible then that row space of B, or the row reduced matrix B, could be a lot simpler to look at and may include rows that have zeros, in which case we can pick fewer vectors. We don't have to necessarily go through the procedure of determining whether the three vectors, the three rows of A, are linearly independent. If you missed what I said, I'm going to show you a nice 4-step process for doing this. Okay, so back to the original problem. The original problem: find a basis for the row space of A. Now remember, the row space of A is simply the subspace spanned by the rows of A. This is simply the span, the linear span of the three rows of this matrix. Okay, so I'm going to go to purple for the steps again. You might want to refer to these steps in your homework. It's very convenient to have this all boiled down to 4 steps, and in the previous procedure for null space, I think it was 3 steps. So step 1 in purple. Step 1 in purple. Find the RREF of A. Okay, that is, take A, find the RREF, and it will be some matrix B. Okay, so let's do it. So we have A, the same initial matrix. I'm tired of writing it. I'm going to take a chance that I can actually use this Surface Pro. Getting a little better at it. I'm just nervous. Okay, it's too much information for you. Okay. There. Probably would have been easier just for me to copy the matrix. Okay, so if we take A and find the reduced row echelon form of that matrix, we get the matrix B, whose rows are 1, 0, 2, -3, 0, 1, -7, and 8, and 0, 0, 0, and 0. Okay, now the theorem we just looked at, Theorem 2.13 says that if A and B are row equivalent, and A is definitely row equivalent to its reduced row echelon form by definition, then the row space of A and the row space of B are the same. So let's pick off a spanning set for the row space of B. This is this RREF, that's B. Okay, so that's the second step. 2. Finding spanning set. Find a spanning set for the row space of B. What's staring right at us? The row space of B is the span of the vectors. Oops, I think I want to go back to black. The span of the vectors 1, 0, 2, and 3. The rows of B. And 0, 1, -7, and 8. So there is a spanning set for the row space of B. Okay, we don't have a basis for the row space of B because of what? What do we need for a basis? We need spanning. We also need what? Linear independence. Step 3, show linear independence for the spanning set in B, for the set in number 2. Show linear independence. Why are those two vectors linearly independent? The vectors 1, 0, 2, -3, 0, 1, -7, 8 are linearly independent since they are not what? Since they are not proportional. Or you could say linear. One is not a linear combination of the other. But for 2 vectors, just say they're not proportional. So these vectors form a basis for the row space of B. So there's only one thing left to do. State basis for row space of A. So, but row space of A equals row space of B. So these vectors form a basis for the row space of A. Okay, now when you do this on your exam, I would like you to explain these 4 steps. Don't just do the row operations and pop up with the basis. I want to make sure you understand what it is you did. Okay, so please. Now I'm going to take a little bit of a side trip here to mention an important result in linear algebra. This side trip for us is not going to play a great role in our work, but nonetheless, it's an important thing in linear algebra. Okay. So before I do that, what is the dimension of the row space of A then? How many vectors are in the basis for the row space? Is 2. Okay. Now, notice that the dimension of the row space of A is equal to the non-zero rows of the RREF of A, equals the number of non-zero rows of the RREF of A. Okay? Now, back to the system of equations in the null space. the number of non-zero rows in the RREF is exactly the number of non-free variables. Number of non-free variables in the solution, to the system of equations AX equals 0. Okay, now remember that the dimension of the null space of A was equal to the number of free variables. The number of free variables in the solution to the same system. AX equals 0. Well, since the number of non-free variables plus the number of free variables equals the total number of variables, we get a theorem, a very, very, very important theorem in linear algebra that doesn't play too much work and a role in our work. Okay, so since the number of non-free variables, plus the free variables, number of variables, equals number of variables, and we have theorem 2.14. Okay, those of you going on with more linear algebra, specifically math majors and some engineers, you're going to use this result in some of your work. We have the dimension of the null space of a matrix plus the dimension of the row space of a matrix equals n, the number of columns in the matrix. Okay. Okay, so I'm going to draw a little red line below that, dotted dashed red line, to end our little side trip there. And I apologize for putting it here in the middle of our subspaces that we were looking at. It kind of doesn't belong too much, I think. But it's in your textbook in this area. And I'd like to correspond as much as I can to your textbook. Okay. Okay, here's our final subspace. Let's consider our same old m by n matrix. So let A be an m by n matrix. The column space of A is the subspace of Rm, because the columns will have m. The vectors formed by the columns of A will have m entries. The subspace of Rm spanned by the columns of A. The procedure for finding a basis for the column space is very similar to the procedure for the row space. It involves 2 additional steps, and the steps make sense. They make a lot of sense. So here's our matrix A, the same matrix as before. So the column space of A is nothing more than the subspace of R3 formed by the columns of the matrix. So it's the span of the columns, or the vectors, the column vectors formed from the columns of your matrix. And 5, -3, and -15. Okay, so just by, oh, I think there's more than that. I think I've skipped one. I think I've really skipped one. Hold on. Okay, that's what I like about one of the few things I like about online teaching is that I can pause videos and fix my stuff. The thing I don't like is that everything I say is recorded. so I can't ever say, no, I didn't say that if I really did. So anyways, keeps things real. The column space of A is nothing more than the span of the columns of A. And just as before, if those four vectors were linearly independent, those four vectors would be a perfect basis for the subspace of R3 spanned by those four vectors, if they were linearly independent. So the procedure, this 6-step procedure, which really isn't that difficult. You think 6 steps is like, oh my God, that's so much. The 6-step procedure is meant to make things a little easier on us. So the first thing is, well, actually, let me kind of give you an overview of how this procedure relates to the procedure we did for the row space of the matrix. If I took the transpose of this matrix, the columns would become rows. So these column vectors, these 4 column vectors, would become row vectors. So I'm going to replace the matrix with the transpose of the matrix, then find a basis for the row space of that transpose. And then what do you think I do to get the basis for the column space? I just take the transpose of the results of that. So that's why it's a 6-step procedure. The procedure for the row space was 4 steps. The procedure for the column space adds 2 steps. First we take the transpose, and then at the very end we transpose the results back to columns. If you missed any or all of that, it's not that big of a deal. So the first step is to find a transpose. Find a transpose. Okay, so let's do that. Super simple. A transpose is the vector, or the matrix 1, whose columns are 1, 1, negative 5, and 5, 2, negative 3, 25, and negative 30, and finally 5, 0, 10, and negative 15. Okay. Okay, then step 2. Step 2 is the first step in the row space. Find the RREF of A transpose. That is, let's take A transpose, do elementary row operations to find the RREF, and we'll call that B. Okay, so I did that. I found that the RREF, so here's step 2 over here, the RREF was, let's see what it is here. I'll copy it down real carefully. The columns are 1, 0, 0, 0, 0, 1, 0, 0, and 3, 1, 0, and 0. So the next step, corresponding exactly to the procedure for row space, is find a spanning set for, now we took the transpose, so we're back into the row space. Find a spanning set for the row space of the matrix B that we found. Perfectly good spanning set for the row space of B. Well, the row space of B is the subspace spanned by the rows of B. So would be 1, 0, 3, and 0, 1, 1. Okay. So next, just like before, we show that these vectors are linearly independent. Show linear independence. So they form a basis for the row space of B. Okay, these two vectors, 1, 0, 3, and 0, 1, 1, are linearly independent since they are not proportional. One is not a linear combination of the other, or simply they're not proportional. Okay, so 5, state the basis for row space of A transpose. Well, I should backtrack a little bit. I showed that the vectors are linearly independent, so they form a basis, I should have said that, for the row space of B. So state a basis for the row space of A transpose. So, but the row space of A transpose equals the row space of B. Why? Because matrices that are row equivalent have the same basis. Okay, have the same row space. The equivalent matrices have the same row space. That was the theorem. So the row space of A transpose equals the row space of B. So these vectors, I might as well name them here, 1, 0, 3, and 0, 1, 1, form a basis for the row space of A transpose. So what do you suppose is step 6? Since we took the transpose of the matrix to do this work with row space, we take the transpose of these basis vectors to get the basis for the column space. We transpose back. So 6. State the basis for the column space of A. We have a basis for the row space of the transpose, so we should transpose this basis to get the basis for the column space. So 1, 0, 3 and 0, 1, 1 form a basis for the column space of the original matrix. Okay. Okay. Well, that ends our the three subspaces that we wanted to look at. I'm going to finish with one more example. This last example is a use of column spaces in matrix theory. There's nothing new here. It's just the same procedure that we did in this last example to do our final example. Okay. Okay. So here's sort of a preface for our last example. Sometimes we need to find a basis for the subspace of Rn spanned by several vectors. This is the same as finding a basis for the column space of a particular matrix. So here's an example of what I'm talking about. Find a basis, a linearly independent spanning set, a basis for the subspace of R3 spanned by 3 vectors. Spanned by the vectors 1, -1, 0, 1, 1, 1, and 2, 0, 1. Okay. Okay. If you really look carefully at these three vectors, you can get an answer. But I want to use our procedure for this. This is the same as finding a basis for the column space of A, where A is given by the matrix whose columns are the vectors in question: 1, -1, 0, 1, 1, 1, 2, 0, 1. So let's solve this problem using the procedure that we did in the last problem. 1. Find A transpose. 1. Find A transpose. A transpose is 1, 1, 2 is a column, -1, 1, 0 is second column, and 0, 1, 1. Okay. Step 2. Find the RREF of that. So find the RREF, and that's our step 2. The RREF turns out to be column-wise 1, 0, 0, 0, 1, 0, and 1/2, 1/2, and 0. And that matrix we'll call B. Okay. Step 3. Find a spanning set for the row space of B. So a spanning set for the row space of B is the row vectors 1, 0, and 1/2, 0, 1, and 1/2, and that's it. In this particular case, just like before, the row reduced echelon form, reduced row echelon form, produced a row of all zeros at the bottom. Okay, so determine that these are linearly independent. These vectors are linearly independent since they are not proportional. They are not proportional. Okay, we're almost there. So they form a basis. For the row space of A transpose. Okay. 5. Since the row space of A transpose equals the row space of B, because B is just a row equivalent matrix to A transpose, these vectors form a basis for the row space of A transpose. Okay. Alrighty, so 6. A basis for the column space of A then is the transpose of these matrices, these column vectors, these row vectors. So the column vectors are, I don't want to put an equal sign there. Hang on a second. It's not correct to put an equal sign there. The basis for the column space of A is the column vectors 1, 0, 1/2, and 0, 1, 1/2. And therefore, a basis for the subspace of R3 spanned by the original three vectors 1, -1, 0, 1, 1, 1, and 2, 0, 1. Therefore, a basis for the subspace of R3 spanned by those three original vectors is the vectors, column vectors 1, 0, 1 half, and 0, 1, 1 half. Okay, so this ends a very long section for you guys. Go ahead and dig into homework as soon as you possibly can. We're done with the most complicated, the most involved parts of Chapter 2. And very soon we'll be starting Chapter 3, the differential part of the differential equations part of this course. But before that, you should get started on the homework for Section 2.4. And I'm looking forward, as usual, to talking with you all again soon.